Welcome everybody to the second in our rebooted series of Saito Social. Today we're talking to Jack O'Connor from the Blake3 project, which is dear to our hearts here at Saito because we make extensive use of it in our code base. So we're just wanting to kind of dig in today and get a better picture of what's on at Blake3 and maybe learn something ourselves as well. So welcome, Jack.
Nice to meet you guys.
Maybe we can start off with a very high-level picture because we can say that Blake3 is a hashing algorithm and we like it, but it probably may not make that much sense to casual listeners. Can you just give us a quick introduction to Blake3?
Yeah, and should I introduce the concept of a hash function? I think
so, because maybe people I'm thinking who watch this will generally understand but they might also think it's pretpretty much a solved problem, right? So they'll also think,
I'd say not entirely wrong.
We can probably take for granted that people know what a hash algorithm, like SHA-256. We're turning
like SHA-256
strings or information into a unique fixed length random string or random number. But I think the differences between different hashing algorithms and why someone would want to come out with Blake3,
right. Sure, right. So yeah, the first thing to know about Blake3 is it's you could call it a drop-in replacement for SHA-256, right? So in its default mode, it outputs 256 bits, 32 bytes, whatever length input up to some gargantuan maximum that no one cares about, right? It's, of course, I say drop-in replacement. It's not the same hash as SHA-256. It's a different algorithm. That's clear to everyone who's played with these things, but not always clear to those of us who haven't. So that is what it does. It has many features. The first thing that most people notice when they play with Blake3 for the first time is it's fast as hell. We tried to kind of front load that in the README. I encourage people to compile and run B3 sum. That's our
if you're as geeky as me, you found the biggest Linux ISO on your machine and then time tested it just to see it run.
Yeah, the Ubuntu install disk. Exactly. I think that's probably the one I've done a bunch of times.
Right, exactly.
You learn obscure facts when you play with this stuff. Like, for example, Windows above a certain number of gigabytes doesn't like to keep things in cache. Anyway, then we could get into this sort of performance benchmarking if we like. But right, so Blake3 on the command line's B3 sum. Sort of, you might know SHA-56 sum. People might know B2 sum was the Blake2 command line implementation. I should clarify that I was not involved in Blake2, but I used it, read up on it, and then got connected with the Blake2 authors. So the first interesting feature of Blake3 is performance. And if you compile B3 sum and run it on a big file, you see that it is in the neighborhood of 10 to 20 times faster than comparable tools, which is kind of nuts. Because all these things are, of course, like very carefully optimized for performance, right? So cryptographic hash functions, like all of our cryptographic tools, like AES, the block ciphers, all of it, really smart people try really hard to make them fast as heck. So, what's up with that? And the answer is pretty much all parallelism. So modern computers, as many programmers in the audience will know, are very good at parallelism. They have all these cores, which can run many threads. They have these SIMD registers that can do lots of arithmetic on one core at the same time. And to really take advantage of that, you need if we were on a blackboard, right? I would draw the structure of the hash computation, sort of like SHA-256, the many traditional algorithms like it use a structure. I'm going to use a buzzword. They use a structure called Merkle-Damgard, which is the two people's names. And that it looks like a chain if we were to draw it. And some people start thinking blockchain, and they're not unrelated, right? That's the idea that you sort of mix things, and there's this chain of the data dependencies there. And you need to not have that structure if you want to be able to do lots of things in parallel, because the nature of a chain is you got to figure out the answer from this block before you can feed it into the next block. And that means you can't parallel.
It's inherently serial.
Right. And most hash functions are inherently serial. And Blake3 on the inside doesn't look like a chain, it looks like a tree. So it's again, another buzzword, it's a Merkle tree, which is an old idea. It's been around since the 70s. There's been a lot of things like it. But for various reasons, which we could maybe go into, it could be interesting. I don't really know, but for various reasons, it hasn't been a common design choice in hash functions. But that's what Blake3 does on the inside. There's another hash that's been published recently that has a tree structure called Kangaroo 12, and I do like to mention them together. There are many different sort of projects in this space. They're all very fast, and as soon as you have a tree, now all of a sudden your leaves no longer have arrows going between them. The arrows go up instead, because of course trees grow down in computer science, which is And so you have all these things that can be done at the same time, and then you can throw all these techniques at it. So anyway, I'm kind of going into a rabbit hole. So we throw threads at it, and we throw SIMD at it.
It's great. I mean, one of the reasons it's really suited for blockchain. I'm kind of curious, and wanted to ask you, I guess we'll get to that, is that for things like processing a large block, there's a lot of hashing, the transaction contents need to be hashed, and we can parallelize those across as many CPUs as possible. And so then the hashing algorithm being able to take care of the ability of the CPU itself to parallelize things.
Yeah, there's some subtlety there. And I wish I knew more about Saito than I do. I sort of read up on Bitcoin back in the day and haven't really kept up with much since then. I was always curious.
Bitcoin, it's the issue for processing big blocks, right? Because you can process the transactions. Yeah. When we do the performance check, the hashing is a huge, huge bottleneck. Because if you've got to do that on one CPU, or you've got to do it serially to figure out.
I think that's something people might misread is, we're not interested. We don't use Blake3 for, it's not the mining type component where you have Bitcoin running on SHA-56. We, in some ways, be hurting things by, or not necessarily improving anything by speeding up your hashing algorithm. It's more to do with the fact
difficulty level would adjust.
You're constantly using hashes to verify things, and in our case, big things. And so that speed improvement is
it's for producing a block, and then it's for verifying the integrity of the transactions within the block. So as you're growing scale, the longer it takes, you're exploding the amount of time it takes to check that this block is valid. So the huge improvements that we've seen. I had a question.
I'm curious about that, actually. So my understanding of Bitcoin is a little bit old, but my understanding is that if you were to replace SHA-56 with Blake3 or something similar on the inside of Bitcoin, it probably wouldn't help you that much, both for the proof of work reasons we already mentioned, which is like the difficulties just scales, but also because the inputs to the hash in Bitcoin are not that long. I don't actually know how big they are, but they're relatively small. And you need like when you start talking with threads, you need megabytes of input. That's kind of the scale. So it sounds like you guys are in a different situation. I'm kind of curious.
We can talk about it later if you want. It's a more scalable design. And what that means is that the amount of data inside the transactions can get much larger. And you can do things like transactions embedded within transactions. I think most of the speed improvements are not from, most of the transactions aren't going to be massive in size. But we're still seeing a lot of it. Should we move on? I wanted to ask you about the Too Much Crypto paper, because my understanding as a layperson is that there's two reasons for the big performance improvements that we're seeing out of Blake. And the first is this parallelization approach. So if you've got a big transaction, you can, the algorithm is going to break it up into chunks, and each CPU core can kind of individually handle them, and then we accrete them up into this is the major hash. There's this
that's roughly
second step you guys have taken. And I'm hoping you can maybe just give us a quick introduction to this Too Much Crypto paper, where you're saying you're looking at SHA-256, you're looking at these other algorithms, and you're saying, well, really, they were developed when we didn't actually know how much security was enough. And there's maybe too many rounds. Could you give us a quick intro to that? And
I could give you a very quick intro to that, and then I run the risk of getting myself into trouble because you guys should get JP on. That's what you should do. But I am not a PhD, and my specialty is not the particular question concerning this.
Okay, so we're gonna blame someone else if it's wrong.
Yeah, so blame someone else for all the mistakes I'm about to say all that. So just to catch folks up, who of course most people probably haven't read the paper. So most crypto, including hash functions, including block ciphers as well, is based on some sort of like primitive block operation that mixes some stuff without loss of generality that describes the overwhelming majority of these sort of symmetric crypto things. And that mixing is usually done in terms of some number of rounds. And when you're designing these things, that number of rounds is a parameter of your design, which you can tweak. You can increase it to do more mixing. And the argument in Too Much Crypto is sort of largely centers on this question of whether the number of rounds that the common primitives we use is excessive. And JP's thesis is that it is, and we baked that into the design of Blake3. So Blake3 takes the Blake2 the sort of 32-bit word flavor of Blake2, takes that compression function, that's the block primitive at the root of all that, and reduces the number of rounds from 10 to 7. And so that very intuitively means you're doing 70% as much work as you were doing before, ignoring complexities like how fast your I/O is and nonsense like that. It's approximately correct. You're doing 70% of the work. So it's whatever the reciprocal is of that, like 1.3 something X faster, that's a non-trivial speed up. And if you're an embedded platform, like with Cortex M0 or something with like no SIMD, no threads, right? That is the only speed up that Blake3 offers you. So it's something. It's actually pretty important for the design, but it is a trade-off. And so we have to make the argument that those marginal 3 rounds were not providing any extra security, compared to not doing them. And you do that by examining sort of all the papers people have published, all the attacks they do. The way these things usually go, and again, this is not my area, but the way these things usually go is for example, you reduce the number of rounds to 1. You take AES, take SHA-256, take Blake3. You reduce the number of rounds to 1, and then you try to break that incredibly weak version of the compression function, which you can usually do. And then you see how many rounds you have to add back before whatever attack you just attempted stops working. Right? And so, and there's different kinds of attacks. You try to produce collisions. You try to various things. And then sometimes when you can't produce collisions are what we really care about with hash functions. Usually, like two different things should not hash the same thing. Collision resistance. There are other things you can do. Like you can try to see whether you can find an input that gives like more zeros at the front than it should. Bitcoin would obviously care about that a lot because the number of zeros is proof of work. Right? So if you could like construct some input that like has some distinguisher, that would be considered if not literally a break of the collision resistance, it's probably a sign that something's not great. So there's all these flavors of attacks. And then everyone with a PhD has all these judgment calls to make about how many of them are relevant and what they indicate. Things like this. And so, JP and Samuel and some other folks who I probably haven't met, took a look at that literature and wrote down their opinions. And there's a nice table at the end that suggests round reductions for different blocks. So, and to clarify, like the way I like to approach all this stuff in my personal work is to take these primitives, these block operations, and kind of squint at them and like imagine that they are accomplished perfectly the goal that they set out to do, which is I will perfectly mix one block. And then we can take that and say like, okay, assuming that's correct, assuming it's like a random oracle or whatever other academic concept we want to call it, we can then build a construction on top of it. That's the tree, that's the Merkle-Dam guard. All these things are constructions on top of a primitive. Yeah. And then we can prove that if the primitive is good, then the construction is good. And that's what I spend all my time doing, which is why I'm getting myself into trouble talking about the first thing. But that's the short story. Did that lead to any questions that you're curious about?
That was great. It actually leads me to a totally different question I was hoping to get to later, which is one of the, it's how do you even mentally think about designing these? What's the level of abstraction? I tend to be a visual thinker, and then every now and then something will click, like you're thinking, oh, how does a regression analysis work? And you can get an image, and then you're like, I understand it. But with cryptography, looking at even the problem space, it seems really odd because you're trying to design this in a way, like if you have a mental understanding of what works, it seems at the same time that you're developing the understanding that you're using to build it, you are developing an understanding that teaches you how to attack it. So I was wondering when you're working on this and when you're approaching it and when you're like, you're building the permutation box, which is 32 bits or 64 bits. And, we're going to mix things up and we're going to get avalanches and diffusions going on. How do you mentally work on this? I mean, do you?
Well, I don't work on the box. It's the short answer. And one of the funny things about that area of work is that the attacks that you do, you start coming into buzzwords like differential cryptanalysis and linear cryptanalysis. And these are things where they're kind of their own field of study. They're really different from anything that I would do in the course of trying to like build a tool. So I'm not very familiar with them.
You're black boxing things on a lower level, for instance, this permutation function. And
that's usually how I think about it personally. Yeah. And of course, I mean, this is why we have co-authors, right? Because there's like so many aspects of these problems, and JP and Samuel are such experts in this kind of low level cryptanalysis stuff. But there are ways. So there are interesting mistakes you can make. We can decide whether this is an avenue we want to explore, but there are interesting mistakes you can make where you take that black box that you assume is good and you try to build a tree out of it. and you do it wrong, and even in fact, the sort of the easy way, the naive way you might do it is wrong, and will actually break the collision resistance of the box. Like the tree will not have collision resistance, even though the box did. So there are some really interesting security mistakes you can make, and I can point you guys to some great papers about this. In fact, I did mention Kangaroo 12 earlier, so that comes from the Ketchak team, the SHA-3 team.
Yeah.
They have some great papers about this.
That's really interesting, because there's this long-standing debate with, again, going back to Bitcoin, with the habit of double hashing, right? Hashing the hash for security, right?
We don't need to do
so
that.
What you're telling me is that could actually introduce, if SHA-56 was designed wrong, that could actually introduce patterns where previously patterns didn't exist.
I don't think hashing the hash would ever cause this problem. In fact, it fixes a problem. I think you guys probably know about length extension.
Right. Yeah.
But if you try to do, I think this is actually an interesting case. Shall I sort of paint it out?
Please.
So I wish I had a whiteboard behind me, and I don't. I just have my wall.
Don't draw.
What you can imagine. So we're going to take our file or whatever it is, right, and we're going to break it up into some sort of chunks or leaves. Usually chunks can be more than one block, but we can ignore the distinction between a block and a chunk. We're going to break it up, and then we're going to hash each of those separately, and that's kind of why we're here. That's good for performance and various things. And then, we're going to like concatenate these pairs of hashes and hash the hashes and so on up to make a tree, right? Hopefully that mental image is clear. Yeah. And if you do that, so if you just do that, like with SHA-56 or something, we have this very important question comes up, which is like, what if you only have one chunk? Like if your short file only has one block or a kilobyte or 64 bytes or whatever your size is, right? If you only got one, what are we doing in that case? And the answer is presumably, you're just hashing that and that's your hash, right? That might be the easy thing to do. That is in fact what Blake3 does. If you don't have enough chunks to need a parent node, you just use the hash of a chunk. Yep. But that creates a problem, because what if I look at your file and I look at the hash and I see like, okay, so internally the first, let's say your file's 2 chunks, and so it's got one parent node. And I look at that parent node. I say, internally, the bytes of that parent node, the concatenated hashes of its children were like ABC 1, 2, 3, blah, 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 whatever bytes. And then I come along and I say, okay, what if I say my file is those bytes? My file can be anything. So what if I just arbitrarily choose those bytes as my file? What's the hash of that? And if the answer is the same, it sounds so trivial. It's like, it doesn't even feel like a mistake. You just violated collision resistance. We've introduced collisions by failing to distinguish between the hashes of these concatenated child hashes, or what we call chaining values, or the hash of like data, which could be arbitrarily chosen to match anything. If we don't distinguish those things, we just broke the world. It's very sensitive, right? It's like, it's so funny. And there are a lot of applications that do this and get away with it because maybe they didn't need collision resistance, or maybe they introduce collision resistance in some other way. They might mix in the length at the top level. I think Bitcoin actually gets away with this. But if you have a general purpose hash, you have to avoid that mistake. So you have to carefully distinguish the hashes of leaves from the hashes of parents. That's basically the thing you need to do. There's another one. Is this going on a tangent?
No, please.
This is a pair of problems that you need to be familiar with when you write a tree. And the Ketchak team's paper treats this with formality and like a proof framework. It's really great. The other side of it is, imagine you've got like it doesn't really matter, a 4-chunk file. So your tree is like 4 leaves and 2 parents and 1 meta-parent, grandparent, whatever. And then you could also imagine an 8-chunk file would basically have sort of 2 of those and then 1 additional layer of parent top, right? So suppose you have a secret file. Maybe this is like HMAC or something, where you've got like key at the front or something, whatever. You have given me the hash of an input that I do not know, and it's that 4-leaf shape. Can I take that hash and kind of slot it in and produce the sort of other half of the tree containing whatever I want, and produce the root node that hashes the thing that you gave me? Can I make it a subtree of a larger tree? If I can do that, that's a length extension attack. Some of the folks listening might be familiar with how SHA-1, SHA-2 are vulnerable to this problem. You can like add more, even if you don't know all the stuff that came before. And that's why we need HMAC. I realize I'm throwing a lot of buzzwords at the microphone, but like, so double hashing fixes that, right? It's one of the ways to fix it. And so like, if you could like slot this tree in fact, maybe I could add more bytes to the right. I could also add more bytes left, right? I could slot your hash in. I don't know whether I'm being mirrored in the video. It's not going to make sense. But I can slot your hash in on either side. Right? This is not even length extension. It's like more general. And so like, to fix that problem, we have to carefully distinguish the hash of a node that I believe to be the root from the hash of a node that I believe to be the interior of the tree. Because that way my root node will never match the correct interior hash of the same data. And it's not useful to you to perform this attack.
That's done by just arbitrarily tagging them, or
So for example, if you're taking SHA-2, you could say like that first problem we talked about, distinguishing the leaves from the parents, will like, append a 1 byte for the leaves and a 2 byte for the parents or something. And then you do this other one by appending a 3 byte and a 4 byte or whatever. You in some way force them to be unique.
The website also talks about side channel attacks. Length extension attacks aren't side channel attacks. No. Are side channel attacks things like these power differential attacks where someone's trying to listen to the CPU? Because I read that and I thought to myself, how on earth, like honestly, how on earth does anyone even start to think about solving this? So
this is also not my area. Which website were you referring to?
I think it's your website. I'm pretty sure it's your website. Is this something that people can make headway at?
Generally, no. You expect any symmetric crypto primitive to not have this problem. Well, I say that. You expect it to not have the problem in terms of timing leaks. And then there's this question of whether anyone can solve it, I think, with power leaks, because it's like the number of 1 bits in your arithmetic unit.
What generally is a side channel attack? Is that an attack on the hardware then, or?
Yeah, this is, I'm going to get myself into trouble by talking about power analysis. It's easier to talk about timing. Is that equally good? So a timing side channel is very relevant. And so when, for example, when I've taught applied cryptography, we do this in class. It's fun to play with. So a good example of this is HMAC. So and like when you authenticate any message with a shared secret, shared password or whatever. Well, I shouldn't say password because that's bad hygiene, but a shared key. Then the way you check that authenticator, we call that a message authentication code or a MAC. That's what HMAC is. The way you check that authenticator is the recipient who shares the key recomputes it themselves, and they just compare. They do an equality check to see whether you've produced the right one, and if you have, then great, the file's authentic. And the idea is the attacker doesn't know the key; they can't produce the right one. That opens up a very common mistake, which is that equality comparison that you do, even if you computed everything securely and correctly, that equality comparison at the end, string equality or byte string equality or whatever, slice equality in whatever programming language, is typically implemented with some sort of loop that like breaks the first time it sees a character that's not the same on both sides. Right? And so if your equality function returns more quickly when the first byte was wrong than if the first byte was right, you have a big problem.
I see.
You have a big problem because now the attacker, instead of having to attack like all 256 bits of your map, which is completely impractical, they're attacking one.
You just need to be
usually byte at a time. Right. Your 256 attempts should give you that byte, and then you march on. And if you try to implement this attack yourself, it like takes an afternoon because the bookkeeping is kind of funky and there's timing, so you probably want to do it in a loop. But you run into all sorts of interesting programming challenges. But it's fundamentally like trivial. I'm not saying it's easy for your homework, but it's trivial from a cryptographic perspective. And it's like, damn, it's another one of those like. That didn't even feel like a mistake. I used the like equality operator in my language. How's that?
Well, it's also the guy who writes the equality operator.
Well, yes,
gets his code rejected if he doesn't optimize for speed, right?
Right, exactly. Right,
Why would he be thinking about your problem?
Right. Why are we messing around here? And so it's a very common mistake. If you look at we don't do this in C because it's just bytes, but in Rust, our library returns a hash type, which wraps some bytes, and its equality implementation is constant time for this reason. We were actually just looking at there's the crate that we use, the library crate. So libraries called crates in Rust. Yeah. The library crate that we use. There's a couple choices, and we use one that we've used for many years. And we were comparing them recently. Someone filed a PR, and we were comparing them and looking at the assembly that gets generated. And we found that this other one was like 100 times slower. I can't remember the exact factors. Like, whoa! Like for some reason, some very bad assembly got generated there. It's a very technically interesting question. How do you compare two strings really fast but also constant time? And that comes up. If you look at, for context that people probably care more about, if you ever use Python and you're like import HMAC in Python or import secrets, which is like the good random number generator, go read those docs. No one ever reads the docs, but you go read those docs and you'll see that they have a like, I can't remember what they call it. It's not called EQ. It's called something, compare digest, I think, something like that. They have an equality function provided for you. And the docs have this big red rectangle that's like, oh, you better use this one. This is why. It's a very interesting topic that like shows up in a lot of like normal APIs. So that's a timing leak. If you get that wrong, it's a timing leak. And that's a pretty easy to understand example of a side channel attack. And it doesn't matter that your crypto was good because you just like leaked the data. It's a crazy way. Really cool. For what it's worth, Blake3 does not really have any particularly unique relationship to this problem. Pretty much any normal hash function would kind of, you expect all the implementation to be constant time. And if you're using a Mac, you need to use a constant time comparison.
Okay.
I had a question, basically, again, from stuff I'd read up on, where you started off writing something called BOW, which was aimed at essentially implementing what is Blake3, but you wanted to ensure streaming, right?
Well, right. So yeah, the BOW project was originally based on Blake2, and that kind of became the Blake3 project. As I pulled in some of the authors, we started collaborating more. We decided that's what it should be. So yeah, can I tell the story of that real quick?
Yeah.
So the original reason I got interested in tree hashing stuff, about everything we've been talking about, was not really for performance. It turns out it's great for performance. That wasn't why I got into it. I got into it for a like kind of related but mostly different reason, which was streaming. So like I was working for a company called Keybase at the time. I don't know if some of you folks like to use that. It has a very special place in my heart. I learned all my crypto at Keybase from Max Crone and from the other folks there. It was a very important part of my time in my life. And we had these encrypted messages. We had a chat application, and it still works, by the way. I'm just speaking in the past tense. It's still there. I don't know if it gets much active feature work now that it's been acquired by Zoom. But so you have this encrypted chat app, and as you can imagine, like the chat messages are like some sort of structure. I don't think it was JSON, but you can imagine it's JSON. It's probably message pack. I can't remember exactly what it was, but some data, and that gets wrapped up and encrypted, and a bunch of magic happens that makes sure it's like authentic. And then, the months pass and you decide to add features to your chat app, and you decide to add like attachments or some files, right? We want to like encrypt files and throw them in there for pictures, whatever. It's like a perfectly normal feature. Yeah. So you're like, okay, what are we going to do? You don't want to throw like megabytes of data into your JSON. It's going to like gum up everything and it's really slow. So you're like, okay, we'll hash it and encrypt it separately, or in the other order, probably. It's actually relatively important that you encrypt it and then hash it. That's beside the point. and then we take that encrypted blob and throw it into S3 or whatever. It doesn't matter because it's encrypted and encryption is magic. And then the hash is in the message. So when you download it, you check it and it's all good. And that works pretty well. The problem is if the file is like an MP3 or a video or the kind of thing you might want to consume from the front without downloading the whole thing in advance, right? Especially on like a phone or something. That hashing step screws you because it's like, even though you can compute a hash in a sort of streaming fashion because there's stream bytes into the hash without necessarily buffering them all, you don't get the answer until the end. And so if you're trying to compare that to the answer that you know is correct, you don't know anything about the file until you've downloaded the whole thing and fed it into your hash. And that's like, because you can use it. It's relatively easy to use encryption in such a way that it's you can sort of stream decrypt. That does work. You can do things with chunking. It's a little bit subtle. There's some pitfalls, as you can imagine. So many pitfalls and all this stuff. But like you can do it. And for example, that's what TLS is, right? So, it's a stream, right? Of course, it's packets and frames, blah blah blah. But you can sabotage that by like hashing it. And so I wanted to have a sort of verifiable streaming hash where you could verify it and do chunks as you go. And we didn't end up doing it at Keybase. Because it would have taken 6 months. And like, we have jobs, right. But it became an obsessive side project of mine. And so what you do is exactly what we've been talking about, right? You build a tree. I mean, this, like I said, these ideas are not new. You build a Merkle tree. BitTorrent does this, right? I think the original BitTorrent format, the torrent was like just a list of the hashes of chunks. And of course, the problem is that list grows in size linearly as the file grows in size. It doesn't scale very well. And then I think some later BitTorrent enhancement like made it a tree so that you just can root, which I think is probably why we can have torrents that are just links. I'm not sure about the details, but anyway, this sort of thing had been done plenty of times. So you make a tree, right? And the idea is that you have the root hash of that tree. And so if you want to verify it, say you want to verify the first 2 or 3 chunks, right? So you'll need those chunks, and you'll need the parent nodes that are over them, and then all the parents over those. So you wind up with kind of a path from the root down to your chunk or your subtree, whatever you're interested in. And that path, these are balanced binary trees, so it's logarithmic in depth, which again, I'm throwing buzzwords, but like it's not that big, and the parent nodes themselves are not that big. They're like a couple of concatenated hashes, and so it's not that much extra data. And what you can do is the root hash, so you can verify the first parent that contains the hash of the second parent, and so on. You walk it down, and you verified everything all the way down, and you never bothered to download most of the file, but you verified what you got. That's verified streaming. And the bow command line utility today does that using Blake3. So to make it work, you can't. Of course, I can't just send you the file because you need those parent nodes. And you can't compute those unless you know the other half of what went into them, which is what you're trying to avoid. So you need to have the sender pre-compute it, usually pre-compute it, and save it as like extra metadata, and then kind of interleave it in a stream. There's a lot of funny.
I mean, we're very familiar with this, but only for the purpose of reducing the size of data you need to transfer. So obviously the classic Mercerized block of data is you say, well, I'm only interested in certain leaves. So I can get the rest of it as just the parent hashes or whatever else, and I can therefore verify against the block hash, etc. But I'd never, funnily enough, I'm very familiar with that. I'd never seen the idea of doing that in streams, which is funny because one of the major threats to a network like Saito is sibling and or just throwing bad data at nodes, right? So if you've got, say, gigabyte or half gigabyte blocks, and someone's claiming this is genuine information that you need, but it's junk, and it's compressed at the very least, so you won't know until you uncompress it that it's full of junk and nothing to do with what you want.
That's even if you don't get tricked, it's a denial of service attack, right? It's
exactly. It's a very obvious attack against a network where one of the things you're looking for is openness and uncensorability. So this is something we're not deploying yet, but of course is now in my mind gone into future development needs because
the interview is stretching into things that we can use Blake3 for.
I push you in that direction. I don't know how much interaction you guys have with IPFS and those folks. I imagine
very little.
Okay, but there's an implementation of IPFS. I might have the details. I think an implementation of IPFS is the right term. I could be wrong. Called IRO, which might be named after an Avatar character, but I might also have that wrong. And they use Blake3 on the inside, and one of the guys working on that has re-implemented the bow detail substantially. There were certain optimizations they wanted to include that I never got around to implementing on my side. So there's some prior art on this, and there's some YouTube videos that have been recorded.
Oh, good. That means we don't need to write.
There's actually probably a lot of good code you can use.
Can I pull back then maybe to Blake3? Because one of the things that you guys talk about is you say, look, there are 3 fundamental things that Blake3 can be used for. The first, I think, is hashing. The second is keyed hashing, and the third is key derivation.
Yeah, there's like 3 functions.
Right. So we've talked about the first, which is hashing. I'm hoping we can talk about the other 2, learn more about what they are, because we've also got some questions about should we really be maybe using Blake3 for this instead? Keyed hashing, as I understand it, it's, well, you've got your hash algorithm, but you add a salt. So your output is going to be...
usually call it a key. I mean, for of course, obvious reasons, it's keyed hashing. But so you made me think of HKDF about the salt.
So you didn't call it salted hashing?
No, you could.
The question I had is, I mean, maybe this is really basic, but with other algorithms, with SHA-256, you take your string, and if you've got a salt, you can just append it to the byte stream, and then you do that, and you're still going to get something unique. Is there something different about why you would have keyed hashing as a feature? Is it faster? Is it better? Are there attacks that...
The short answer is it's faster and it's very natural to do it. But there are interesting subtleties to your question, because of course, SHA-256 is famous. SHA-2, SHA-1, and MD5 are all famous for having these length extension attacks that make what you just described surprisingly dangerous. So, you take your key and you prefix it to the message. Length extension means that the attacker can like compute new max that he doesn't have a key for. And if you suffix it to your message, it's better. But you run into interesting questions about what happens with collision resistance. There's some funny interactions with collision resistance where you might expect a keyed hash to be safe, even if collision resistance has been broken, as it has for MD5. But if you suffix the key, it doesn't do what you thought it was going to do. This is all like in the weeds, because like we just don't want to reason about our hashes if collision resistance is broken. But we do think about these things. So that there are subtleties. Every modern hash since the SHA-3 competition, and every modern hash, I predict for all of time, does not allow length extension. We now recognize that to be a mistake. They knew about it back in the day. They just didn't consider it important, I think, is the story from SHA-2. It's very easy to fix. You just have to do something different in the final step so that the output you just show to the world is not the same as what you would have used if you kept going. And so we do that, and SHA-3 does that, and every hash from now on will do that. And so with these nice modern hashes that don't have this length extension problem, you can just, ideally, I think, prefix the key. It helps with that collision resistance stuff I was hinting at. Of course, the problem is that advice is really bad for all these old hashes that we still use. It sucks. It's like you want to give that advice, but it's like, it's...
Okay, so the takeaway for people like Richard and myself are either you can use a modern hash and you can suffix the salt, or you should...
I would say prefix as the thing to memorize.
Sorry, prefix.
It's so hard to tell people to memorize this because it's like you have to use HMAC. Anyway, sorry.
Put it before. Put the salt before.
If you were using SHA-3, that's what you would do.
Yeah.
Yes.
Okay. Maybe can we ask about key derivation as well?
This is actually the key derivation API is very near and dear to my heart. I thought a lot about that back in the day, and I wrote a lot of that stuff about it. It's a very long section of the paper. I was very interested in solving a problem that comes up. You guys have probably run into this. Like whenever you're working for like a cryptography company and you have a lot of custom stuff, there's a lot of features and things are changing, and like it's often the case that you like. Back in the day, you negotiate some shared secret with whoever you're talking to, and then you like did some stuff with that secret. Maybe you encrypted something. And then a couple years later, you're like, we're adding some features. We want to maybe encrypt different things that are domain separated from the first thing, or we want to use it for macking or some other use, or we want to derive some other stuff for it. So you have this value that's already in use with some algorithm. And if you want to use it with some other algorithm, we're going to derive a signing key from it. Who knows, right? If you want to do that, the official and correct answer that any cryptographer worth his or her salt will tell you is that you must use a derivation function with different context strings such that the two subkeys that you're using are unrelated to each other other than being derived from the same root secret. And then they're guaranteed not to have any interactions, and life is good. And of course, the problem is that 2 years ago, you decided to use that root secret directly in your application. Yeah. And you can't, maybe you can't like just go back and like be like, we're actually going to hash it again or something, because you'll break everything. But you want to, it's like, what do you do? So it used to be that the answer was you just sort of roll the dice. You're like, okay, we're just going to like hash it with SHA-256 and maybe a context string and call that an unrelated thing. And the gamble that you're doing when you do that, the dice that you're rolling when you make a decision like that is you'd better hope that SHA-256 isn't like an internal ingredient in the thing you were already using, right? If the encryption that you were already using does a SHA-256 hash of your secret and like the message or something, like throws that on the wire, like, well, you just published the thing that your new feature considers secret, right? This is why cryptographers give you this advice. Like, just don't risk it. You have to know everything about what everything's doing. And then you have to ask really crazy questions like, if I'm using the secret as an RSA key over here and as an AES key over here, which is a ridiculous example, but are there any interactions between those two things? And the answer is like, no. Everyone knows the answer is no, but like, there's not a paper out there that says it's no, and there are really funny examples of this. My favorite example is HMAC and HKDF. So HMAC is what we were just talking about. It's sort of like prefix the key and double hash to avoid these length extension problems. It's a MAC. It's very commonly used. HKDF, key derivation function similar to HMAC. You can kind of plug any hash into it, and you get this like key derivation function takes a bunch of parameters, the salt in the context. You may or may not know that HKDF is defined in terms of HMAC. That's what it is. Like you go read the code or read the spec. It's a couple of calls to HMAC, or in a certain obscure mode that is not often implemented, it is a single call to HMAC. And so if the first application of your key was HMAC, which is a perfectly reasonable thing for it to be, and the second you're like, oh, we should derive a subkey, and you throw it into HKDF. Like, did you know that? Like, no one knows that, right? The tools are hard to use, and we don't support like common scenarios. So this is all the back. So I was thinking about
it can't warn you.
Yeah, it's like, how do you publish your interaction with future algorithms that have not yet been published, right? Yeah. It's a hard problem. So what we did is we're like, okay, we're going to put in this derived key mode. And functionally speaking, so it takes 2 parameters instead of 1. So it takes a context string and the stuff that you're hashing, which we usually call the key material. You call it, maybe it's a root secret or something, a shared secret. And it hashes them together, right? And it is functionally exactly equivalent to hashing the first thing with the regular hash and then using that as a key for a keyed hash of the second thing. It's a pretty natural, you could call it naive way of doing it. The crucial difference is there's a little field of bit flags in the internal Blake3 state. And so when we do and it's not a public field, it's like part of the spec. It's sort of like the initialization vector constants, or there's no like argument for that. It's just like hard coded. This is part of the spec. It's not public. And when we do those 2 steps, you hash the context and then you hash the keyed hash, the key material. We set bit flags that we never set in any other circumstance. So those 2 operations are guaranteed to be domain separated from any other use of either hash or keyed hash.
I see.
And so you have to break the collision resistance of the hash function to produce a collision, right? No 2 inputs that you can easily select will ever do that. And so we take that property. So derived key is domain separated from the other things. And then we add documentation that says, and I put this in bold typeface every time I type it. The context string parameter to this function must be hard coded. We say it should be hard coded, application specific, and globally unique or something like that. But basically, you must hard code this value. You must not take this from a database, from the clock, from user input, or like this must be hard coded in your application. Yeah. So if you violate that rule, well, then you and I might find us some circumstance where the input supplied to whatever. But if you don't violate that rule, that plus presumably you don't happen to choose the exact same context string that your like coworker did without telling you. Right? Just choose a long one, right? Like, and it's hard coded. So this is that plus the domain separation that we built into it means you are guaranteed not to interact with whatever they produce. And that's true even if they're not calling derived key at all. They're just calling hash or key hash or some other algorithm that's built on top of those things. Because derived key is guaranteed to be separated from those things as long as they didn't violate the documented security requirements. So it's this ridiculously niche problem that I believe we all run into as soon as it's like our day job to write this stuff. Yeah. And I was like, someone should solve this problem. And there's nothing really specific to Blake3 that makes it any better at this than any other hash could have been. But we just decided to publish this 3rd function that that's the little thing on the inside. Yeah. So then you get into arguments with people who want to.
I've learned. Anyway. We should be prefixing.
Well, that's the problem is I can't tell you which one to memorize because of the length extension problems. The true answer is there's no good answer to that question. Which sucks, and it's our fault as cryptographers that we're in this position. But such is life.
The good news is I don't actually think we do any suffixing with.
I'm more of a if you use Blake3 or SHA-3, you're fine.
Yeah. Could I ask you a question? Maybe Richard, did you have any questions about?
Well, actually, I'm about to get myself excommunicated, so I should roll back. There is a good answer to that question, which is to use HMAC. It's just a tragedy to use HMAC with functions that don't require it, like SHA-3 or Blake3, because you're paying extra compressions for no reason. Anyway, sorry. So to unexcommunicate myself, I will mention that is the correct answer. It's use HMAC, even though it's like a slightly obsolete answer.
That's good because we can't edit this. It's all live.
Your membership of the Church of Cryptography is safeguarded.
They're sticklers.
I've got a couple more questions. Richard, did you have anything about key hashing or key derivation?
Not specifically, no. I just learned something.
I kind of wanted to pull into what you were just saying about the compression and the extra cycles. It's one thing I find really interesting in the blockchain space is there's very little actual overlap between economics and comp sci. People think there's a lot more overlap than there actually is, but people tend to fall in one of the either two camps. And we see it in things like the trilemma arguments, where a lot of people on the comp side, they approach it as a technical problem. That we've got these three things and we want more of one or more of the other. And in the economic approach, you can kind of boil things down and say, well, really, it's about you've got a limited budget, or you've got a certain amount, processing a certain amount of bytes gets you a certain amount of money, and you've got that to spend on stuff and scale. And the reason I'm kind of making a longer intro is that when we approach the scaling problem economically, and when people talk about things like trilemma solutions, the scalability of Trilemma, there's a lot of, oh, well, we've solved it this way, we've solved it that way. We look at it and we say, well, actually, the only thing that really solves it is a fundamental efficiency increase in getting the same security, doing the thing for the same budget. And so from my perspective, looking at Blake3, it's actually one of the strongest arguments for this is actually a Trilemma solution, because it seems to be an unambiguous increase in speed while holding security reasonably constant. So the question I wanted to ask you is, that's a sales pitch for Blake3, by the way. The thing I wanted to ask you is, from our perspective, looking at this, is this, from you looking at the field, is this like a one-time thing? Are we on a linear, further improvements? There's maybe some linear grind where with, CPUs will get more registers and will be more efficient at caching, but the space is all known. Are there things out there in the future that you're aware of where you're like, well, quantum computing might change this, where we might actually get radical improvements in the speed of hashing? Or
it's the opposite, right? It means we're forced to use much more expensive algorithms, unfortunately. Yeah, I don't. It's interesting. So I have to admit, and I tell my students, when I have students, I tell my students to be honest when they don't understand something. I don't know what the trilemma is. Is it like CPU and network and disk space or something like this?
It's popular because of the classic software quality trilemma, right? Where you budget, time, etc. And I think it reflects on it. But the idea is basically it's a notion of decentralization, security, and scale. So those three are always in conflict.
Let me. You've got a set budget. You've got transactions paying fees, and the amount of security you have scales with the return on investment you provide the people that do the security function. So you can pay for stakers, you can pay for miners. And then you've got the classic scale versus decentralization, because you've got to run computers. So you can run a lot of weaker computers, or you can run a smaller number of really strong ones. And it confuses people because people think, well, if we get more scale, then we've got more money and we can spend more money on things. But it's like, yeah, but the marginal fee is lower, and so your dollar per byte goes down. So that's the economic view of things. So it's things like, you can buy a certain number of CPU cycles, but if the network has to pay for itself, you can't simultaneously run more computers and increase decentralization at the same scale unless you're reducing the payout to the people that are doing the secure work function, or you're running fewer computers. And so most of the solutions actually cheat on this. They'll say like, well, we're going to force you to run this kind of machine in order to participate. But what that means is your costs go up, and so the amount of money that your profits go down, security goes down, that sort of thing. People don't often think of it this way. I think in comp sci they conceptualize it as, well, the problem is like sharding. And so you do things like you're breaking up the state, and you've got now two shards instead of one, right? Like you're breaking the assumptions that every machine is processing every byte, for instance. Anyway, so in that sense, the efficiency sense, I actually think that Blake3 is a really good example of an efficiency improvement, because you're using less CPU cycles. You've slightly reduced the rounds. Parallelization is also
parallelism is the key there. And I can't comment intelligently on most of the stuff you just described, though I would like to learn more about it. But in terms of what you can look forward to, parallelism is the big one. And so you could say that Blake3 gives you unlimited parallelism, and the biggest way that is not true is you need to have enough input to take advantage of whatever degrees of parallelism you have. But so assuming you have enough input, it's a functionally unlimited amount of parallelism, which is cool. And the sort of degrees of parallelism available to us are increasing rapidly over time. So our SIMD register is getting wider, 512 is becoming more common. Core numbers are going up. Things are moving onto the GPU. I've seen people try to implement it on the GPU. It seems it's actually, unfortunately, because it's a hash function, your data bottleneck to the GPU ends up being the issue. It's like it could go faster, but it can go faster on your data. There's a lot of things like that when you get into the weeds. But you can look forward to like the gains, the returns from parallelism going up. That is almost certain to happen. That's nice. Algorithmically, at least with Blake3, for example, we're kind of already there. There's not much of a barrier other than having enough input to feed the beast. And so I predict, I don't know if Blake3 will be the next big standard. I would like that, right? I'd like to believe that.
We would also like that.
I do believe that whatever the next generation of standards will be, I think they'll be looking back on what Blake3 has done and what Kangaroo 12 has done and some others, and seeing like, oh damn, like 10x. Like usually we're like fighting tooth and nail for 10%. Like 10x is wild. It's like, well, yeah, we didn't do it. It's like the SIMD did it, but but you have to allow it. So I think the writing's on the wall for the future of things like hashing algorithms, and I think it's a very interesting point of comparison. You look at like ciphers, like what are what's the most common cipher? ASGCM. Right, that's your most common like TLS cipher suite, or ChaCha20, Poly 1305. It's similar in the following respect, which is that like they chuck everything up into blocks, and then the processing of those blocks is completely parallelizable. That's been true for a long time, and it has to be, because that's our bottleneck. The funny thing is, you don't usually bottleneck like a network system on hashing. It's usually encryption, decryption. So they were way ahead of the game. That's why CTR mode, if you guys know that buzzword, has been so dominant for so long. It's like it's equally secure and fully parallelizable. It's like, whoa, that's pretty great. So I think that you're just going to see more and more of that. I don't think that's going away.
Just a sideline that occurred to me as you were saying that is there. I mean, obviously, it's very famous that Bitcoin mining has made a huge market for ASIC chips dedicated to SHA-256. Is there such a thing for Blake3 yet? Is that a possible B exist? I
think so. I have a Google search alert for Blake3, so that I see like papers that come out and stuff, and 90% of what I see is like cryptocurrency stuff, talking about such and such miner or such and such network, and I am mostly just reading. I see stuff coming down the pipeline.
The most interesting will be someday you'll just start getting a bunch of Chinese.
I was wondering whether to mention that half of it is already.
It's like some dude in Shenzhen. Yeah, I remember my first Bitcoin meetup. I think I told you, Richard. They had the ASIC, and it was kind of like everyone's like, "Oh my god, we got dedicated hardware." Yeah. So I guess
the reason I got to that is thinking about things like encryption at rest for file systems like CFS or whatever, where obviously it's the encryption is now being moved to the people are building processes for file servers that natively handle the encryption decryption, because that's primarily what the operating system is doing if you're serving files off encrypted drives, and wondering then encryption's a big part of that, but hashing is as well, because ZFS does ungodly amounts of integrity checking.
Right. OpenZFS has Blake3 at least as an option. I don't know how hard it is to enable. I was very proud to see them pick that up. I think their defaults are non-cryptographic hashes. I don't know the details here. So maybe a collision's okay because you're then also going to do
another check anyway,
or it's okay if you do more work or something like that. But if you want cryptographic dedupe, something, I think Blake3 is a good option. It seems to be working for them. Our C implementation, which is what most callers pull in, has an ungodly amount of assembly, and there's macros in those headers that are pretty nasty. And so every so often I see GitHub issues where people are having trouble building stuff, and I want to help. But it's portable C. It does a lot of assembly. It's pretty hard to write. But it's it was really cool that they picked it up. I think Bazel was another adopter that I've seen go by, which was pretty impressive. Like they obviously, Bazel likes to hash everything all the time and see if it needs to rebuild stuff, and so you just constantly hashing big files over and over again. It seems like a great use case.
I've got a couple more questions, but Richard, do you have?
Shoot, that was my.
Okay, change of topic. I'm curious about genealogy, right? Because we know there's Cha-Cha and we know there's Blake and then there's Blake2.
Yeah.
And you talked a little bit about this. I'm just curious. I mean, it sounds really ad hoc. Like, why would you say, okay, well, look, Blake3 is developed from Blake2? Is it the genealogy of how, like, the permutations are
Yeah, I was wondering
designed?
about this.
Is this a dead
Yeah, it's that
Roberts
situation
where
the block.
Yeah.
So it's, if you just like look at the code, you could read the papers. It may be less obvious, but if you just look at the code, if you look at an implementation of pick a Python or something like nice and simple, slow, and you look at the code of a Cha-Cha implementation, and you'll see like the same like mixing operations in the rounds as Blake2, as Blake3. So the DJ Bernstein is a big name in cryptography and did an enormous amount of work to make Cha-Cha as fast as possible in software. Like that's what it's optimized for. It's like given the capabilities of CPUs, I don't think it was actually originally optimized for SIMD very much. It's a little bit. I mean, Salsa was the original, and Cha-Cha and Salsa's, I don't know, probably SSE2 was around then. I'm insulting him and implying he's old. I don't know how old he is. But so it was designed to be fast on CPUs with doing arithmetic and you have instruction level parallelism and various things that you want to throw in there. And he just, hammered the crap out of it and made this beautiful function that solves all these problems in this very, very nicely optimized way. And then the authors of Blake, I think JP is the only one who's been on all three papers. I don't know the other authors of Blake, but they took that mixing function. So of course, I should clarify that as a stream cipher, the input to the mixing function in Cha-Cha is like a counter. It's not like arbitrary gunk. It's like a key and a counter. It's sort of like AES-CTR. And so the Blake authors tweaked it a little bit. They added a sort of arbitrary input parameter and they kind of added a few mixing operations to kind of plug it in. But the overall structure of the mixing was unchanged. These extra interleaved operations, that was the only change. And then Blake2, similar, was like tweaks on top of Blake 1. And then Blake3 was, you can say tweaks on top of Blake2. And the higher level details, like the tree structure is totally different in Blake3. But the primitive is very similar with the tweaks. So if you look at the code or the papers or the math, and it's the sort of the G function is the arbitrary name for this thing that gets called 16 times or 8 times per round, whatever it is. It's the same G function with maybe a minor tweak. So the genealogy comes out when you look at it at that level.
Okay, Richard.
No, that was also one of mine. So happy for you to pick. We've got a doc here with the questions and stuff. So you pick the next one to come out.
Yeah, I want to give you the chance. Is there anything? I've got only a couple more. This has been a really interesting call. I'm curious. We know Zuku, from his work.
Zuko, yeah.
He's mentioned things about Blake3 becoming a standard. I mean,
he's big on Twitter.
Are you seeing this?
We need him here at some point.
Are you? Well, one question is, are you seeing this? Question two is, are there things that we should be doing as users to kind of promote the project or help it in a way that?
Oh, that's very kind of you to ask. I mean, reporting build issues when you have them and taking our fixes such as they are is probably the best thing. As long as it builds for everybody, we're doing pretty well. I don't know about standards in general. One thing we have been trying to do is to get someone to kind of stamp a number on the spec. There are, for example, getting it included into OpenSSL requires it to have I'm going to use the wrong term, like a standard number or something like this. Yeah. And I think there are different venues that qualify. So we've been trying to get one of those. And standard spotties are, they are designed to solve certain problems and publishing new standards quickly is not the problem they're designed to solve. But hopefully that'll happen eventually. I'm sure someone will find it interesting enough to stamp a number on it. At this point, to be clear, the test vectors are written in stone. I mean, the output will never change. If you change the output, you have to change the name.
Yeah.
But so probably just get kind of stamped as is, and then hopefully we can get it into OpenSSL. I would very much like to do that.
They're being much more rigorous since the issues they had with versioning and stuff, and just trying
very
to get
reasonable.
people to
very reasonable. And I'm sure everybody and his dog wants to get their algo into OpenSSL. I'm sure that they have a spam problem. and I'm happy to go through the process. It's how it works.
Cool.
I've only got
one last one, David, because we're coming up on the hour. So
yeah, I was just it's not really a technical question. I'm wondering, it's kind of this weird cryptography. It's this weird political space in a way. We see it in blockchain. There's a lot of ideologies around like libertarianism, and there's a lot of paranoia. I'm just wondering if it affects you, if it's the sort of thing where, or like temperamentally, you're like, whatever, I don't care.
I mean, I have my libertarian leanings. I did various things in college, kind of thing. Does it affect me? No, I find that, I've been lucky. Like, it's funny, a lot of spaces on Reddit, various, Bitcoin forums can be a little bit, hard to enjoy. But, if certain filters, like forcing you to clone a Git repo and run make or whatever, it's a small enough number of people who are willing to do that like most of the spaces are pretty small and people are pretty polite. And I've been very pleased. I'll give a shout out to the Rust community, which is like this paragon of like I don't know, discussion health or whatever. It's I think they inherited a lot of that from Mozilla, which had an interesting and maybe unusually healthy culture, at least on the sort of like individual side.
We use
their business model has these issues, but
we use Rust as well. It's lovely, and then you hate it, and then you love it again.
Oh, see, I spend actually the majority of my time right now putting together like videos and blog posts teaching Rust, which I really, really enjoy. Totally drunk the Kool-Aid. So if you guys ever want to do it,
no, it's one of those things. I think there's something that when you come through it, but initially watching someone, I've long said, initially watching a developer learning Rust, it's like watching someone in a mildly abusive relationship, because they sit there saying to their monitor, "I did what you said. You asked, and I tried to please you.
Right.
Why are you never happy?"
Brian Cantrell has a couple of really good talks where he makes basically this point. He's like, "But you said to put the lifetime on the thing," and it yes.
Once you've been through that, you kind of either Stockholm syndrome or genuinely
honestly,
in love.
the lifetimes. I think I looked at your video channel. I think you have some videos on it.
I do.
I found lifetimes the hardest.
It is. I as a rule of thumb, I will tell anyone who's in their first year of Rust, or if it feels like your first year because it's still hard, which is fine. Don't put lifetimes on structs. Just don't do it. Like sometimes you have to put a lifetime on your function signature. You're putting a string in a vector, whatever. Don't put it on your structs. If the compiler's telling you to put a lifetime on your struct, use like a string or a vec or some owned type instead of that. That is the gradual introduction to the language.
Okay. Interesting. And Richard, do you have anything else? If not,
I think something just occurred to me from the previous discussion, but I think maybe we should wrap that up because we're on the hour and we want to try and keep this, punchy and neat. Thank you very much for your insight and the time. It was really enjoyable from my perspective.
Yeah, and also thank you for the work. I mean, it's every day. Yep. It's we're using it. I think, as I said, it was 3-4 years ago we were doing the benchmarking. We were looking at, and it was just unambiguous.
Well, that's right. We should come back. You mentioned right at the start. I mean, that's one of the big things for us is just processing our mempool and processing our blocks, and it just makes such a difference to be able to get that throughput of hopefully one day millions of verifications, hopefully in seconds, and to do that we're going to need all the speed we can get. So
that's what we like to hear. It feels good to hear that.
Great. All right. Thank you very much.
Thank you.
Catch you guys next time.
Next time.